Video, we're going to dive into the aldol condensation mechanism of this reaction happening over here. We're going to we'll talk through each step with the curved arrow mechanisms and explain why this trans product is our major isomer. So we're going to start with our base over here. This is potassium hydroxide, which is a relatively strong base. The hydroxide over here, although it's not showing in this drawing, but it should have a lone pair over here, giving it a negative sign. This lone pair over here will be attacking our alpha carbon. The way to that indicate which one is our alpha carbon, basically our alpha carbon is the carbon adjacent to our carbonyl carbon. So this is our carbonyl group over here, therefore making this our alpha carbon. This is also could be our alpha carbon, but due to the drawing of this reaction, we're going to use this one. Carbon originally in this product, it has two, or in this reactant, I apologize, it has 4 bonds. 2 of them are shown in the drawing and 2 are not. So this is bond 1, 2, and there's 2 more which I'll be drawing right now, which is it's attached to 2 hydrogens, 2 bonds with 2 hydrogens, and these are alpha hydrogens. So this is our alpha carbon and these are alpha hydrogens, or the hydrogens attached to our alpha carbon. As we said earlier, let's get rid of this. So this lone pair over here will attack this alpha hydrogen. Let's do this one. Therefore, the electrons in this bond over here will transfer over our alpha carbon. This step, the results of this step, let me draw it down here. So step 1, the results of step 1 will be our reactant over here. Then we have our carbon over here, and now this bond over here will transfer to be a lone pair over here, give us this carbon, a negative reaction. Let's draw our other hydrogen, and then we'll have this, our OH group, our hydroxide group. Now, the presence of this lone pair over here and this negative sign, which is basically this is our conjugated base, will make this product a nucleophile. So this product will be our nucleophile. Now, our nucleophile will be attacking the electrophile. To identify the electrophile, it's this compound. So this compound is going to be our electrophile. And basically that's because we have our carbonyl group over here, which is going through the inductive effect, which basically means that this oxygen over here is more electronegative than this carbon over here, resulting in the flow of electrons upwards. So the oxygen is attracting the electrons more, the shared electrons between the oxygen and the carbon, more than the carbon, therefore making this oxygen giving it a partially negative sign, and this one making it partially positive. Hence, it's our electrophilic. So this carbon is electrophilic. Therefore, this, let's do blue again. So this lone pair over here will be attacking our carbonyl carbon. Now, since the bond forms between our alpha carbon over here and the carbonyl carbon, the electrons between the double bond, between one of the bonds over here, let's do this one. Let's do yellow right here. Will flow over the oxygen over here. The oxygen originally had 2 lone pairs. Now we'll have a third one, giving it a negative sign. Since this is an acidic workup, it's normally to have protons or hydrogens flowing around. And because of that, this lone pair over here will be attacking this hydrogen, forming a bond between them. So let's draw everything we talked about in this following step. Let's show that on paper. So let's do this. That's what we had earlier. Let's make it a little bit better. Our oxygen is over here. Now let's use blue to draw our new formed bond. And it's gonna be, oops, with this. And now let's draw our oxygen with our newly formed bond with the hydrogen, and this gives it a negative sign. This group, not the hydrogen, the whole group, and this basically right here. And then let's finish drawing our compound over here. Now, as you have the presence of another base right here, this, the lone pair on the oxygen, will be attacking, oh, I forgot to draw our alpha hydrogen. The other one will be attacking this hydrogen. And this will result for the bond, to the breakage of the bond over here. This bond, the breakage of the bond, the electrons from this bond will transfer over here. And as this happens, this will cause this to be our leaving group. So this, the electrons from this bond will transfer over this oxygen, and this is going to be our leaving group. So let's put this here. Again, let's draw this. Let's maintain our color coding to make things easier. So the oxide group has already left. We have and now let's show the formation of our second bond, which is going to be right here. And of course, let's not forget our hydroxide, our ethyl hydroxide group over here. As you can see, this product is our end product, which is our organic product, and it's formed in the trans form. This reaction, which is an aldol condensation reaction, it can be formed, it has two geometrical isomers formed, which is cis and trans, but the major and the dominant product will be a trans form. It will be in the trans form, which is basically what we have right now. The way to identify if it's trans or cis is just by looking at the highest groups, which is we have the carbonyl group, and then this benzyl group, and then we can see that they're not in plane, they're in the opposite plane. This one is pointing up, this one is pointing down, meaning they're in the trans form. The reason why the trans form is the major form or the dominant form, because it creates there is less steric hindrance between them. If they were in the same plane, then there will be more steric hindrance, hence it's harder to be formed. That's why the trans form is the major form. This reaction, called aldol condensation reaction. And whenever we have a condensation reaction, our byproduct or the inorganic product will be water or H2O. And as we can see, this is formed in this step over here. The hydroxide attacks the hydrogen, forming a molecule of water. So I hope this was helpful. Thank you.